All right. Now we're going to try it the way I was taught for the Merchant Marine. Ultimately, the difference here is going to be instead of making the vector triangles here, we're going to make it at the contacts. Meaning we're going to have to make 3 total triangles in separate locations. However, doing so will make it less crowded because everything will be independent of each other. I do think later it makes it less convenient for you, but we'll get to that later on. For the time being, we're just going to construct each of these triangles there. And what that means is we're going to use the M1 to M2 as equivalent to our RM vectors. Importantly, we're not using the 5-to-1 scale because we didn't set this problem originally in the 5-to-1 scale. For the Merchant Marine, when they're using their radar transfer plotting sheets, they just pick one scale, and that scale is true for everything they do in the problem. They don't have to convert lengths between different units. You know, here we're talking about nautical miles out here, but then when we get in here, we're talking about knots, not nautical miles, and we're using different scales. Here, everything is going to be set to the 1-to-1 scale because that's what we chose at the beginning. What that means is you don't even necessarily need to calculate the speed of relative motion to begin with, other than to find time to CPA. So if we move to contact A, we could relabel M1 as R and M2 as M. And now this is both M1 to M2, and it's also the RM vector. This is not perfectly representative of the speed, or this is not like a 1-to-1 representation of the speed of contact A, the relative speed of contact A. Because remember, these were taken 6 minutes apart. So this is how far the relative motion of contact A will go in 6 minutes. We previously calculated that to be 0.8 nautical miles, but it doesn't mean necessarily that this is only 8 knots within the context of this triangle. It doesn't apply otherwise. And because we're going 15 knots, we're going to have to convert that from, just 15 knots at the 5-to-1 scale to how far we would go in 6 minutes as well. Now, likewise, it's not that hard. 15, 6 minutes. If we connect the two, we're going to get 1.5. But it's always good to double check. Passes perfectly at the 1.5 mark there. So in 6 minutes, we would go, if their relative motion goes 0.8 miles, we would go 1.5 miles. We do have to remember which directions are which in the vector triangle. If we're going to now plot on our ER vector, it's going to be E to R. So even if we're going this way, it's actually going to go, we're going to draw the line the other direction because we're starting with R. You'll see what I mean in a second. So we measure our line now to be equivalent to the ER vector that we plotted at the beginning. And now we slide that up to contact A. And we draw the line this way, in the opposite direction that we're actually headed. Because now what we can do is we can plot E somewhere back here, and we would get ER going the correct direction. So remember, we're going 15 knots, so we would go 1.5 miles in 6 minutes, which is right there. Measure it out. Right there. And there's our E value for contact A. And now, because we have E and we have M, we can connect the two together, like so. And if we now slide this down, all until we get to the center, and then shoot it out, we get 235. So we calculated a true course of 235 degrees. If we look at our previous problem, we got 234.5 there. So that's really close. It might as well be the same. The difference there is negligible. And if we measure our speed, well, we know that this isn't necessarily its speed, but this is the distance that contact A will go in 6 minutes, which, if we measure out, is 2 nautical miles. Because it went from the 3 to the 5. That's 2 total nautical miles. Now, as usual, 20 to 6. Guess where this is going to intersect? Passes straight over 2. Or, sorry, I did that wrong. 6 and 2 will take you to 20. I got ahead of myself because I knew the answer was going to be 20. So true speed, 20 knots, which I believe was exactly the same as we got. Yeah, 20 knots. All right, now we'll do that with contact B. So now we take, oh, by the way, we can also now pretty quickly put on our little ship right there. And you can see it is facing basically the same way as it was in the previous problem, or in the Navy method. Now this is more accurate to its exact heading because I kind of just threw this down generally the way it's going, but it doesn't matter that it's not perfect. If it was a little bit like that, that doesn't change the rule situation necessarily. So now on to 2. Remember, we're going to now label M1 as R and M2 as M. We're going to take our course and speed. I'm going to run into the same problem I did before here. I nearly hit the stand. Take our course and speed. We're going to slide it all the way down. Plot it out that way, because remember, we're going E to M. And now, thankfully, we don't have to measure out 1.5 miles again. From here, we can just take the exact same length of the ER vector that we found from the first for contact A, and we can just apply it now to contact B, right there. And we get E connect the 2 together. Now we're going to slide this all the way to the center of the scope so we can measure what that angle was. And we get 29286. We get a true course of 286. And if I recall, we had 283 as the true course in the Navy problem. Close enough. So now that we've already got that, we can now draw our little guy. To find the speed, we can measure that, take it to our scale, and we get my divider's a little damaged, so I could feel it spreading out. Just under 0.7 miles. Just under 0.7 miles is going to come out in a true speed if we do 60 D Street to 6.8, 6.9 knots. Compare that to the 6.5 we got in the first one. Now finally we can carry this over to contact C. We measure out the ER. Here, firstly, we label R and M. And we slide ER all the way up till we come into contact with the R. draw it across there. Then we measure out the same 1.5 that we've been using. Place it here. And we get our E value. We connect the two. There we go. It's always difficult getting the exact perfect angle. And we slide it down. We got 178. So a true course, 178 degrees, which is exactly the same as we got before. If we measure out our speed, bring it over here, and we get 1.25 miles, just between the 1.2 and the 1.3. So that's gonna get us the true speed. If we wanted to do the scale, we could, but it's gonna be 12.5 knots. I believe we got 13 in a previous problem. And then we just draw our triangle. So that's how we do it. The Maritime Academy method. Ultimately, what we get is the exact same picture in both. We've got three contacts here, this way, this way, this way. We know their courses and speed. We got them essentially identical between the two. They're still going the same directions on the same speed. It doesn't matter whether you do your triangles out here or you drew your triangle in the center, unless you're being tested on it. For the Navy, they keep these things as legal documents, so it kind of has to be uniform. In the event of a collision, they want to see you doing it exactly the way you were taught. That way, they can monitor, or they can very quickly figure out what you were doing right and wrong. Merchant Marine, first of all, in reality, you're never actually going to be doing this. You're just going to stick with ARPA or navigate by eye. But in the classroom setting, your teacher might want you to do it exactly the way I've shown here. Whether or not you prefer the other way, it depends on them. Whichever one you prefer, clear it with your teacher, with the mate, and confirm that they're fine with one or the other. And if they're not, if they want this, then learn how to do this well. I'm going to do all the problems in the future in both to alternate between the two. But realistically, you should be able to do either without a problem. There's no difference in the amount of work. Here, you don't have to move around as much. You keep everything in the center, but it gets kind of cluttered. Here, everything is clear which ship you're worrying about. And technically, you did the same amount of total work, but it is going to get more frustrating when we go into changing course and speed, because you're gonna have to do that for all three of these instead of just doing it once on here. We'll get into that later.